Hello everyone, welcome to our another video in the series on mastering data structures and algorithms. I am Dr. Prashant K. Gupta. In the last video, we talked about the multidimensional arrays. The concept of today's video is the sparse matrices. Sparse matrices is a term that often involves the use of matrices, and matrices are derived from our mathematical counterparts. So let's see how. This is a brief introduction about myself. There's a link to my website and it contains most of the information about me. By passion, I am a researcher and a teacher. So first of all, what are the matrices? Matrices, as in mathematics, they are having a similar meaning as in C programming. Matrices means either the vectors or a two-dimensional data organization. Vectors means the values are organized in the form of a linear array. There can be either the row vector or a column vector. By row vector, we mean values organized in the form of single row and n number of columns, same as our linear array. And in column, we have values organized in the form of m number of rows and a single column. So kind of they can be assumed as the transpose of a linear array that we have seen so far. Matrices, on the other hand, are analogous to the two-dimensional arrays. An important term is the square matrix. A square matrix is basically a matrix with n number of rows and n number of columns, that is equal number of rows and columns. Or another way of saying is a matrix that has one row or one column is also called a vector. The matrices in itself are not much importance to us. What is more important are the sparse matrices. Sparse matrices are those that have very high proportion of zero entries. These are the two examples of the sparse matrices, the triangular matrix and tridiagonal matrix. In a triangular sparse matrix, non-zero entries occur on the main body diagonal or either above it or either below it. If they occur above the main body diagonal and on the main body diagonal, it is called an upper triangular matrix, like example shown over here. You can see. Since by joining all the elements, it is forming the shape of a triangle. That is why it is called a triangular sparse matrix. Similarly, all the values on the main body diagonal and below it are non-zero, and on the other side are all zeros. That is why it is called a lower triangular sparse matrix. Tridiagonal matrix, on the other hand, has non-zero entries on the main body diagonal, above the main body diagonal, and below the main body diagonal. Rest all other entries are zero. Now the challenge over here, similar to the two-dimensional arrays, is how to store a tridiagonal sparse matrix in the memory, and how to find out the index of an element ajk when they are stored in the form of a linear array. So let's see. Now when we start storing these elements of a sparse matrix in the form of a linear array, we begin from the first element a11, first element, first row, first column. Then we store the next element a21, then a22, and so on. We keep on progressing further till we reach an, that is the last element. So this is how these elements respectively are stored over here. First value stored at the first index is a11, then at the second index a21, and so on. So now you can actually see in every row there are exactly the number of elements which is equal to the number of rows. Like in first row we have one element, in the second row we have two elements, and so on. In the nth row there are n elements. So therefore the total number of elements in B will be equal to the sum of all these values, that is 1 plus 2 plus so on till n, that is n plus 1 by 2. Now you can see actually this is almost half as many as the two-dimensional array of n cross n. Now again, since we are storing all the values in the form of a linear array, now the challenge is to find the index L in terms of G and K, that is BL is equal to AJK. Now the process is very simple. We just need to count the number of elements in the list, including and up to AJK. So now you can see, as I was just now explaining, in any row you can see there are exactly, in any jth row, there are exactly j number of elements. So therefore, before reaching the row j, I would have stored the elements, first element from first row, two elements from the second row, three elements from the third row, and so on up till j minus elements from the jth row. So therefore, and upon reaching the jth row, before ajk, I would have stored exactly k minus 1 number of elements. So therefore, number of elements in the jth row up to and including k will be equals to k. So therefore, total number of elements, as I told you, in j minus rows will be the sum of these values, that is j into j minus 1 by 2, and k will be the number of elements in jth row up to and including k. Therefore, the value of this index comes out to be sum of these two values, j into j minus 1 by 2 plus k. Now coming to the tridiagonal matrix. Over here, we are initially storing two values in the first row, or to be more precisely, three values in the second row, and so on till we reach ajk. So except the first row, every other row will have three values stored. So therefore, you can see when stored in the form of a linear array, first value to be stored is a11, second value to be stored is a12, and progressing so on further till we reach ajk. Now again over here also the challenge is to find L in terms of j and k, that is BL equals to ajk. So now progressing, as I told you, we are having two elements in the first row. In the second row there are three elements, so on till j minus 1th row. Every row will have three elements. Now when coming to the jth row, before the jkth element, the number of elements in the jth row up to and including k will be k minus j plus 2. So therefore, once we add all these number of elements, we can get the index of ajk. So therefore, the index of ajk comes out to be L equals to 3 into j minus 2 plus 2, where this term accounts for the total number of elements in j minus 2 rows just above the jth row. First row has two elements plus k minus j plus 2. So this figure comes out to be 2j plus k minus 2. Now the maximum number of elements that we can store in a tridiagonal matrix and are non-zero can be found out using this. Since only non-zero entries occur on the main body diagonal above and below it, so therefore we have n non-zero elements on the body diagonal, n minus 1 above it, and n minus 1 below it. So therefore the total sum comes out to be 3n minus 2. Thank you all for watching this video, and don't forget to subscribe to our channel. More and more good videos will be coming up soon. Thank you.